יונתן התעניינו על כל מיני דברים בקורס, עברתי לנו תרגיל, ומעבר לזה שזה לא הדרך היעילה לעשות את זה, הייתי מעדיף שתדברו איתי ולא מיונתן, אני לא יודע למה כמה אנשים הגיעו ממני. לפני שיש שם תלונות על הקורס, על התרגיל, על התרגילים, שזה אנחנו פה. לפני שאתם רצים לראש קורס כאלה. אני לא יודע, לא מעניין אותי מי עשה את זה, אבל באופן כללי אנחנו פה באמת לשאלות שלכם. רביד הוא מתרגיל חדש, הוא חסר ניסיון גם עם החומר וגם עם האנגלית. אני יודע שיש הרבה דברים שאפשר לשפר אצלו, אבל אני יודע איך לעשות את זה תדבר איתי קודם. Okay. Now, as you know, in principle, I'm not going to be here for the next 2 weeks. So, if nothing changed, I'm not going to be here for the next, from Wednesday till December 12th or 13th. I understand that most of you are not going to be here on the 13th. So the next class is going to be not next Wednesday, but 2 weeks from next Wednesday. Yeah. Okay. So in principle, I left Ravid a lot of material to work with you. I asked him to be a lot more friendly in the sense that and he's going to give you the lecture notes or his notes before the class, and I actually urge you to look at it before the class. And if you have questions or complaints or anything that is not clear either during the class or the lectures or the recitations or whatever, please let us know first. I mean, this is much more effective. Now, I'm not sure that he will be able to do 4 continuous recitations. I actually gave him a lot of stuff to cover, but at least one of those 4 classes are supposed to be dedicated to your questions. So solving problems with exercise or whatever. So please prepare those questions. Anything that you think you want some clarifications or whatever, let us know. No, it will not be new material, but it will be it will be new material because a lot of what I'm saying here is too abstract. I mean, you need to see it in concrete examples. So we are going to do a few things that I want to do in the exercise. I did it in the past in the exercise. It's not a big problem. But so we're going to talk about maximum likelihood estimation in many cases. We're going to talk about maximum likelihood estimation when there is no when there are hidden variables, we call EM. We're going to talk about at least 2 other subjects. I mean, the notion of okay. Before I talk about what is going to happen, let me continue what we talk about, and then I'll tell you more or less what I expect to happen in the next 4 lectures. But there is still a small chance that I hope will not happen, that I will not travel. So let's see. Okay, so so anyway, this Wednesday there is a recitation of exercise, and then we'll see. So we started to talk about again, we're talking about estimation or parameter estimation. We talked about the estimation as some sort of a chain from a parametric space to observations from which we generate an estimator. So the estimator, so there is some sort of parametric family here. We generate observations. Sometimes we assume that we have a prior over the parameter space. This is in general some sort of an m-dimensional real space, but can have all sorts. It's usually a continuous subspace or Rm. That's what the way we think about it. This process is usually generating a sample. So we're talking about IID samples. And when we talk about the likelihood function of the parameters, we usually think about the probability of the sample given the data. And actually, we often look at the log likelihood function. And we denote this function, by the way, by L of theta. So we actually think about the log likelihood function as a function of the parameter, not a function of the sample. So this is so the log likelihood, this little L, which is also in Amir's notations, is the log likelihood. But it's given the data a function of the parameter. Function of theta. So this is somewhat confusing, but we think about this as a function of theta when the sample is given. A sample is given. Now, the estimator is essentially a function. So this is theta hat is a function of the sample, which is supposed to be a good estimator of the parameter. So this looks very much like actions in the Bayesian frameworks. These are observations, and this is the model. And we essentially, so to do this, we need the cost function, and we looked at essentially two cost functions which are important. I'm just saying it again, just for those of you who are not exactly with us. One is the square norm, which leads to the MSE error. So essentially, it's how far in the norm L2 squared the estimator is from the parameter. And this eventually led to theta hat being the condition expectation given the sample of theta, or the condition expectation. So this is the MSE. And we talked about the other important type of cost function. This was 1 and this was 2, which was essentially 1 minus delta. And this led to the maximum a posteriori, which was the argmax of the likelihood with respect to all the thetas. And or theta prime, if you want. Now, a relaxation of the map was theta maximum likelihood, which was sorry, this was the argmax of theta given the sample, the posterior, and theta maximum likelihood was indeed the argmax of the likelihood. So the difference between these two things is only if we take into account the prior or not, and this is what we call the maximum likelihood estimator. Or the ML, yeah. So this was essentially, and then we actually showed last time that theta ML, we proved last time that one theta ML is consistent. And what was this all about? Just to make sure that you're with me. So this was essentially that the limit, so this is an asymptotic property, that in the limit n goes to infinity, sample size goes to infinity, the maximum likelihood estimate is indeed the right theta. Now this means the right theta, which means the right theta from which this sample was taken. So theta belongs to this class, and I'm giving this number. So this was under some conditions which we call identifiability of the model. In general, what we actually can prove in general, even if it's not identifiable, is that in the limit, this probability, px given theta hat, px given theta of the sample, this is the same as px given theta. So this is a slightly relaxed version of the consistency requirement, but here I don't assume identifiability. I just assume that I can prove that, so this is what we call weak consistency or consistency without identifiability. So this is true only if the model, if theta is a identifiable model. But this is rarely the case in large models. So we usually don't want to assume it. Today at least I don't want to assume it. So this is a weaker condition. It's not that theta hat goes to theta, but the probability condition on theta hat is the same as the probability of theta. The way we prove this, well, there can be many different thetas that generate the same distribution or almost the same distribution. So this, and the way we prove it actually by showing that in the limit, the KL between the data, I mean, P x given theta hat, sorry, Px given theta and Px given theta hat in the limit, this went to 0. So this is again theta hat of xn of the sample, and this went to 0 when n goes to infinity. Okay, so that's what we showed last time. And actually, something nice that comes out of it, which I didn't have time to explicitly mention, is that theta ml, in general, is the theta that minimizes the scale distance between the parametric family between the data. So this was, in general, I can replace this not by the true distribution, but by the empirical distribution. So this is the arg min over theta of the DKL between what I call the empirical distribution, I'll define it in a second, of x given theta, the empirical distribution of x, whatever it is, and the parametric family. This looks a little confusing because so here this was actually in the limit of large n. This was the true distribution. But in general, this goes to an empirical distribution. So what do you mean by empirical distribution? So what's not clear? Yeah. So this is the DKL or the KL divergence. Yeah, and this is empirical, yeah, sorry. I think that Amir write this as just PE. But, so P empirical is a very important thing. I mean, so this is actually the data that you see. So so we assume, here I assumed already that P empirical went to the true distribution. So this is the limit. So P empirical is what? Is actually, you see data. See data and you don't know where it came from. So usually what we do is we bin it in, or we do an histogram, or we do all sorts of things like this. I mean, essentially we look at the empirical distribution of the data. The way I would like to write it, and this is going to be a little bit strange, so I have a sample of size n, the empirical sample of size n, and this is essentially the probability, I go from 1 to n, of delta x minus xi. And I want to explain this notation. So the empirical distribution, this is the empirical, is essentially 1 if I saw a data point in this place, and 0 if I didn't see a data point in this place. So this is essentially the sum over my sample. So the sample is xi, yeah. Xn is, just to remind you, is this long sample, 1 up to xn. So this is essentially delta, or delta functions on my sample. Now, what we actually showed last time, that in the limit of large samples, this particular delta, it's kind of a little bit formal notation, but I want you to understand it. So essentially, when I put my data on my sample, these delta functions are going to accumulate. And eventually, when I have infinite samples, it's going to converge to what? To the true distribution. Okay, so this is, I'm sorry, this is 1 over n here. I have to average it.
Why would it converge to the true?
Okay, so that's a good question. Let me explain it. So what we call the empirical distribution, this is actually an important notion. I want you all to understand it. So we have data. Let's say I have a die which have outcomes 1 to 6, integers, and then I start throwing it. Let's say I throw it 100 times, or I don't know, 60 times, and I got, I don't know, 9, 11, 10, 7, 8, and so on. Some histogram. Okay? So empirical distributions are, so this is empirical distribution, which are, in practice are some sort of histograms. So let me so what do you mean by histograms? So first of all, this is approaching eventually the true distribution of the data, and if it was actually sampled from one of the thetas, it's going to approach this with the right theta. Yeah, okay. So this formal definition, I want to explain it a little bit. So what do we mean by? So again, let's say that I have a discrete variable. Okay, so just let's say 1, 2, 3, 4, 5, 6, like outcome of a die, 6-phase die, and I threw it, let's say 100 times. So my n is 100, and it had some empirical distributions here. So let's say I get something which I can write as a histogram. Okay, so this is just to make things confusing, but I have 6 bins like this. So this is the number of times. So this is the number that I appears. So what I actually wrote it as the number that I appears. It's the same thing. So let's say 1 appears once, sometimes 2 appears some other number, 3, and so on. So what is the empirical distribution in this case? It's simply going to be, okay, so pi, empirical distribution of I, is simply the number of times I appeared divided by n. Okay, so this is what we usually call empirical distribution. Okay, I simply count how many times each outcome appeared, and then I normalize it to make it look like a distribution. So this is the standard classical frequentist approach to empirical distribution. Now, what happened if I have a continuous or many outcomes like this? So this is what I call a histogram here, by the way. This is called a histogram. So a histogram is essentially just binning my data into bins. In this case, I have 6 bins. It's not the nicest picture, but that's what I mean by that. Okay, so there are 6 bins. This was N1, N2, N3, and so on. And 6. Okay. Now, empirical distribution are what we see all the time. I mean, these are what we do in experiments. I mean, you do some certain repetition of an experiment, you see n times n1 this, and now what happens if x is real? What would you do? So let's say I have a variable which can take place between 0 and 1. So this is my x. And now we start to see all sorts of numbers. 0.33, 0.51, 0.75, and so on. You see numbers here. How would you? Okay, so I see. Let's say I see a number here, and I see a number here, and so on. I see all sorts of numbers. Let's say, okay. Usually these numbers are not going to repeat. But if they're real valued, the probability of having exactly the same real value is essentially 0. Let's say that there is some smooth underlying distribution here. If it's not smooth, then it's a different story. So I have some distribution, let's say uniform distribution, or some, I don't know, some distribution underneath. So if it's smooth, I'm going to see these numbers are going to be very different from each other. But that's the data. The data is this number appears once, this number appears once. So essentially, the sum of the delta functions is telling me, okay, so put a delta function on this. This is x1. This is another delta function on x2. Put another delta function on x3, and so on. So obviously, this is not it's a very non-smooth distribution. I mean, it's just a list of pulses like this. So what we usually do, we widen them somehow. I mean, so we say, okay, one way of doing it is essentially binning them. So let's say I have 100 samples, so I divide the interval into equal bins. Let's say divide the interval into intervals of size delta equal 1 over 100. So this actually is too fine binning for 100 samples. So usually the number of bins should be much less than the number of samples, because you want to have an histogram in this bin. So essentially, this is something which we call discretization. You actually divide this interval into intervals of size delta. So in this case, if delta is 1 over 100 and this is 0, 1, I'm going to have 100 bins like this. Is this clear? And then you simply count how many times my values actually fell into one of those bins. When I do this, I move this problem of the real value into this one. Now I have an histogram, okay, of only 100. But let's say I know that I discretize my variable sum. So if, let's say, I have 10 million samples, maybe with 10 million samples, I can have a much finer bin. Okay, so essentially, the trick here is to essentially bin the data into bins which are small enough to. So essentially, what I do here, I approximate this distribution by a discrete histogram. This is something like this. And eventually, so this is some sort of discretization of my smooth distribution. And in the limit, in what limit? In the limit, in this particular limit, that n goes to infinity, I do two things together. I increase the number of samples, and I refine the bins, make them smaller, such that eventually this histogram of discrete values is going to approach my smooth underlying distribution. Now, the way we like to think about it mathematically is something like this. I mean, so essentially, what I do is I put a delta function. I mean, I put an impulse or pulse of size 1 on every one of my samples. And then in order to actually generate a histogram with it, I integrate this. Remember, delta functions mean something only inside integrals. Outside integrals, they're meaningless. So essentially, I integrate it with some sort of a window. This window is essentially my bin. So I can integrate it with the bin of size delta, which is essentially a unit distribution centered on delta. Then when I integrate it, I get this. This is going to be the histogram. Now, the windows can be not necessarily rectangles. They can be Gaussians. They can be anything. This method in general of taking a histogram and turn it into what we call a nonparametric distribution, sometimes called Parson windows, or there are many, many names for this. So essentially, what I do here, I take this sum of delta functions, integrate it with the window, and then I get a histogram. In this case, the window was a pulse of size delta and width of a height 1 over delta and width delta, such that integrated to 1. So this is my window, or sometimes called or bin or Parson windows. So all different names for the same thing. So this window is essentially telling me how am I going to bin the data, and then I integrate this window. Let's call it age of x or something like this. so the histogram, or let's call it W of x. Okay, this is the window. So the histogram h of x is essentially the integral of this empirical distribution with the window. It's actually the convolution. It's the convolution of the delta function. There's the window. So you know what convolution is? Yeah, you heard it before. So it's a convolution. Let's write it. It's a convolution. The histogram is a convolution of the window with the empirical distribution. So that's a general. So this is a function of x, and this is this, the sum of deltas. And this is going to generate a histogram. If the window is a rectangle, it's going to be bins like this. If the window is a Gaussian, it's going to be a smoothed version, and so on. And in both cases, when the window size, has a size delta or some type of characteristic size, when the window size window goes to delta, when the delta, this size goes to 0. But that's one thing that I require from these windows. But of course, what delta should I actually choose depends on the size of my sample. Just like binning. I mean, I want my bins to be large enough to have enough data in each one of them, and small enough to actually approximate my distribution. I'm not sure this is clear to everyone. I mean, I see all sorts of blank faces here. So if this is not clear, ask me. So this is something quite important in general. I mean, you see data coming from a real valued or any valued variable. In order to see something like an empirical distribution, you need to bin it. You need to count enough. So formally, this is just an integral of this sum over delta functions with the true with my window size. Now, yes.
What's the whether this is not this is a non-parametric distribution?
I didn't get it. What?
I think you said it's a non-parametric distribution.
Yeah, it's a non-parametric in the sense that I don't have any parametric family underneath in general. I'm just approximating my distribution by something. This is usually called non-parametric. Yeah. So all this type of binning is non-parametric. Unlike the family, the parametric family that we talk about all the time. I mean, the Gaussians, all these are already smooth. So the non-parametric can be anything. So again, we can talk a lot about non-parametric estimation and non-parametric. This is just just one glance at it. Non-parametric. So usually, a parametric distribution. I mean, your canonical example is a Gaussian. Okay. So this is a smooth distribution which has two parameters, and it's completely smooth. I mean, so if I have mu and sigma, it gives me a positive number to any point on the real. Okay. But empirical distributions are usually not like this. I mean, you see numbers here and there. I mean, actually, all these numbers actually have a precision. They have some width, but so this is a parametric distribution, like all the parametric families that we discussed so far. Here, I don't know. It doesn't belong to a parametric distribution. It's essentially just a set of bins or a set of windows like this, and eventually it can converge to anything if I have enough data. That's what, so since actually it is parametric in the sense that there are delta and W essentially define some sort of very high dimensional parametric space. So where exactly I put the W's and what are the size of them. So there are, even in these non-parametric families, there are in fact parameters of the windows, which I slice through the data. Okay, so that's in general what we call non-parametric histograms or Parsons windows or empirical distributions. Yeah.
What do you mean that the window goes to
Now, what I mean is that this function of x, when the width of the window goes to 0, this is usually should approach a delta function. So that's a requirement from these windows, which means that, okay, so if, let's say, if it's a rectangle window like here, if delta becomes very small, it's normalized to 1, yeah? So the height is 1 over delta. And if I decrease delta, this will go to a pulse. If this was a Gaussian, shrinking the width to 0, it's going to approach delta. So all these windows usually approach delta when they become very, very narrow. Okay, so this is just one very short introduction to what we call non-parametric method. But now I just wanted to show you, so formally, when I plug this empirical distribution in the DKL, so what is the DKL? This DKL of some empirical distribution, as I just defined it, with the parametric family, with some theta. So that's what I said there. So let's just write it down. What is it? So in general, this is the integral of this distribution, P empirical of x, log P empirical of x divided by P x given theta. Okay, that's just the definition of the KL. In this case, it's continuous variable. Okay, so this is usually, so far I think I wrote sum over x. Yeah, if you remember, dpq was in general defined like this, log p over q. So now I generalize it to integral, and I do this. So okay, so what is this? So again, so this I can write as the integral over x of p empirical log p empirical, which I actually don't care about. So this again, if x of x dx, so this is something which is independent of theta, minus the integral over x of p empirical log px theta dx. Okay? Big X here is just all the possible values of the domain. Okay, so again, forget about this. I don't care about this. But now I plug here the empirical distribution. So what is it? It's going to be minus the sum over n, the integral of 1 over n, the sum that I goes from 1 to n, this delta x minus xi. I just formally do it. This is p. Log px dx. Okay, so this shouldn't scare any. I'm sorry, plus this. I just denote this now as h minus h of p empirical, but it doesn't really matter what it is. Okay, so it's minus h of p empirical, which at this point you don't care about. So what is this integral? So I can take the sum out. So this is minus 1 over n, the sum. And then I have the integral of a delta function with the log. Okay, so it's an integral of delta x minus xi, log of px theta dx. What is this? What does a delta function does to an integral? You just take the integrand at this value. So it's altogether going to be simply minus 1 over n, the sum of the log of pxi over theta. Okay, and that's precisely up to this constant, what we call the log likelihood of the data. So you see that minimizing the DKL, yeah, that's what I wrote here. Minimizing the DKL of the empirical distribution with respect to the parametric family is just like maximizing the likelihood of data. This is a triviality, but it's okay. So what is interesting about it?
What happened to the x?
And this is independent of theta. Yeah, sorry, there's plus this, yeah, minus the h. But then when you minimize, you don't care about it. Minus respect to theta. So you take the derivative with respect to theta. The minimum is independent of the constant. So this please proves this h empirical. Okay, so this is some number. I don't care. At this point, I don't care about it. Yes?
And what is the conclusion?
What is what?
The conclusion.
The conclusion is just a proof of, I just proved this. That essentially, the maximum likelihood estimate is the minimum, the arg minimum of the KL divergence of the empirical distribution with the family. That's what I did. Just proving this. So this is the proof of this. Okay. And now, so it's something you should be able to see yourself. I mean, so essentially, I just plug this. This is why this definition is useful, because when I plug it into the integral of the KL divergence, I get exactly the line. Okay. Any question about it? Still not clear. Now notice that what we actually do here is some sort of a projection. I take the data and I look at the closest point to the data in the KL sense in my parametric family. So this is something which we'll come back to later on in the course. Maybe much more advanced. So essentially, if what I'm saying now is not entirely clear to everyone, tell me. So essentially, there's some sort of a manifold of distributions, which I call P. All the parametric family. So points on this manifold are distributions. Okay, so this is the parametric family, whatever. So it's lying in some in Rn. But for every point on the manifold, there is a distribution attached to it. That's the meaning of the parametric family. Okay? So this is subset of Rn. Usually we think about compact subsets, but it doesn't really matter. So this is some sort, I mean, so there's an Euclidean space Rn somewhere here. And this is the parametric family. So this is, usually we talk about smooth parametric families. What do you mean by smooth? Where did I assume it? Take derivatives, take to theta, and we actually mean that this makes sense. So this is a smooth manifold. Okay. I don't know if you are used to such geometric thinking, but so there's a manifold of parameters. It's actually usually a curved manifold. So it's usually not something like a plane, or it can be a very, very funny thing, but it's curved smooth manifold. And essentially, when we have data, so this is the empirical distribution, what we just showed is that the maximum likelihood estimate is finding the closest point in this manifold. So this is going to be the P maximum likelihood for this particular data. So this is a projection. So this is what we call a projection. So this P maximum likelihood was the arg mean of the empirical distribution to the parametric family. So this is another way of writing it. I take the empirical distribution and I project it on the family. Project in the sense, so a projection in general, and say a projection, let's say, of this point on the floor, it's going to be the point on the floor which is closest to this point. Okay? Closest to the Euclidean sense. So this is a projection. This is a projection, sometimes we call it E-projection, of P empirical on the family P theta. Yes. Okay, question. So this is a projection. So I minimize the distance. So if I call this is not really a distance. But if I think about it, this is 0 if they're equal. Otherwise it's positive. So it's some sort of a projection of this distribution on this family. So it's the point in the manifold which minimizes out of all the other points I mean, this is the one which is the closest distance. So it's really in some sense the intuition of a projection. The only problem is that the KL is not a distance. It's not symmetric, and doesn't obey the triangular inequality and many other things that distance usually obey. But it's still what we call a distortion. It's not a metric, but it is a distance in the sense that I can minimize it, and it's uniquely defined. So in some sense, the maximum likelihood estimate is a projection from my empirical distribution to the parametric family. That's what I just showed. Okay. Yes?
Minimize the decay.
Yeah, the DKL. The DKL with respect to the first argument. So here is the empirical and here is the family. Later on we'll talk about the other side of projection. Well, I project this to this. And this will actually give us something completely different. but we'll come back to this. Some people already heard it from me in some other cases.
And so the distribution is 1 point?
Yeah, so usually this is unique. It's 1 point on the, it's 1 point in the family, but of course, if the family is non-convex, so for example, if the family, so that's a very good question. So in general, let's say that my family is something like this. It's a non-convex family, and I'm here, so there can be 2 points, 1 here and 1 here. Both of them have the same distance. So in this case, so this is unique only if it's a convex family in some sense. Otherwise, not unique. But still, okay, the maximum likelihood may not be unique. You should know this already. For example, if my family is not identifiable, then there can be 2 distributions which are essentially the same distribution in 2 different places in my parametric space. But in general, it can be non-unique in a much worse case, much worse sense. It can be infinitely many maximum likelihood points. Some of them are closer, some of them are further, and so on. So as long as this is a convex family, this projection is unique. Yes?
The DKN we calculated before, the P empirical and the real P.
Yeah.
So it's supposed to go to 0 when n goes to infinity, right?
Right. It will go to 0 when n goes to infinity if my distribution is actually in the parametric family. Yeah. Then this will eventually go to.
I'm asking about the expression disregards when you.
Yeah, you're absolutely right. I mean, so this, when I said this, I didn't assume that P empirical is in the parametric distribution and in parametric family. But if my data was in fact taken from the parametric family, then this happens, that the P empirical approaches the true Px theta for some theta. And then, of course, the distance will be 0. So in this case, my empirical distribution will actually converge to the true point, to a single point, or one possibly single point in the manifold. In general, by the way, maximum likelihood can work even if your data is not taken from the parametric distribution. For example, you can model things by a Gaussian, even if the underlying distribution is not a Gaussian. And then the likelihood that this distance will never be 0, even in the limit. Okay? Yeah, if it's not. Let's say that I have data which actually is taken from Poisson, or taken from, I don't know, a mixture of 2 Gaussians, but actually I'm trying to model it with 1 Gaussian. So then I can get the closest point, but it will not be identical. It will not be 0 distance. In this case, of course, the notion of consistency doesn't make any sense. Okay, I want to go on because I'm spending too much time on it. So I remind you that we talked about, in principle, the probability for any estimator. We talked about the probability distribution of the estimator given theta. So essentially, we have this probability distribution of the estimator, which was taken from some data, conditioned on theta. And this was something which I denote like a Gaussian. So this is here. This is the theta axis. In general, it's a multidimensional, but I can't draw much more than one. And so this is how this P of theta hat given theta looks like for a certain n. Okay? And then we talked about 2 things. So first of all, the maximum posterior is this point. Okay? The map. This is the, it's not really the maximum, it's the most likely value of theta hat. Now it can be, the conditional expectation is the mean of the distribution. And so on. Okay, but in general, for every different estimator, there is a different distribution like this. And then we talked about 2 other things. The 2 other things were the bias and variance. Just want to remind you. So what was the bias? Yeah, so the bias or just of theta hat given theta, or just B of theta hat given theta. So what was it? How was it defined? Yeah, so it's the expected over theta hat given over the samples, given theta of theta hat, which is a function of the sample. So this is a random variable minus theta. Okay, this is what I call the bias. Okay, so essentially, if it's unbiased, then essentially the average is always theta. Okay, so the mean of this distribution is always going to be theta. Okay, this is unbiased estimate. And then I said so the bias is essentially how far the mean is from the true theta. And the variance of the estimator was what? Just like any variance. How is variance defined? The expectation of the square distances to the mean. Yeah. Okay? So this is, again, the expectation with respect to the samples that are taken from some theta of the estimator minus the mean of the estimator. Again, with the same expectation. Square. Okay? So this is the variance. The variance is always any random variable is the square deviations from its own mean. Okay? Average. And then we said something that the mean square error, which is essentially of theta hat given theta, is essentially the expectation, again with respect to the samples given theta, of what? Of the estimator minus the true value of the parameter square. This was the mean square error. Notice the difference. Here I actually take the distance to the true parameter, and here I actually took the distance to the mean. And then I showed you that this is simply the bias square plus the variance. Okay, so this was something I showed last time. And then we actually said something quite important, that if we are talking about unbiased estimators, then what? So then the thing that minimizes the mean square error is exactly the thing that minimizes the variance. Okay, because if they are unbiased, this is 0. So the variance and the mean square error in this case are going to be the same. And then we showed, I need more space for this. I take it here. So then we showed, it's too long to talk about this empirical thing, but it's all right. And we showed that for any unbiased estimator, for theta hat unbiased estimator, which means that b theta hat theta is 0 for any n, the variance of the estimator is what? Was greater than, again, you're not, 1 over n, this is n times j of theta, where j of theta was what we call the Fisher information. J of theta was defined as the expectation with respect to x of the log, what we call the Fisher score, the square of the logarithmic derivative, and the logarithmic derivative is something which we call the Fisher score. So this is just and this is called the Fisher information. I'm sorry, אתה מפריע לי. או שאתה תגיד את זה בכל רם שכולם ישמעו, או שתגיד את זה אחר כך. Fisher information. Okay, so the Fisher information was defined like this. And what I want to do next, after the break, is first of all to explain a little more about the Fisher information. It's actually a very important notion. and show you that it's actually related to the second derivative of the score in respect to theta. And then I'm going to prove something quite important about the maximum likelihood estimate, that it's not only consistent, as we already showed, but it's actually what we call efficient, which means it achieves the minimum variance or inequality in the Cramer-Rao bound. So this is what we call the Cramer-Rao bound. And what I want to do right after the break, much faster than I did it so far, is that the maximum likelihood estimate for theta ml in the limit of n goes to infinity, the variance of theta ml is going to be equal to 1 over nj in the limit. This is what we call asymptotically efficient. So efficient estimators are those that achieve the bound here. We'll define them after the break also, how exactly it happens. And then I'll show you that the maximum likelihood is actually efficient. And this really gives the full glory of the maximum likelihood estimate. I mean, it's consistent and it's efficient in the sense that it achieves the minimum variance. Any questions about this particular thing, about the Cramer-Rao bound? Yes? What's your name, by the way? Louis. Yeah. Okay. Yeah, so this, I wrote theta n here. So this is the estimator from n samples. And the estimator for n samples, eventually the variance goes to 0, like 1 over n. But j was defined for a single sample. Okay? And I actually showed it last time very quickly. When you have, if this is a full sample, then this is simply n times j. Because the expectation of the log is going to sum, to change to a sum, and all those sums average exactly the same number. So it's exactly nj. I'll come back to this if this is not clear. So again, we'll take the break. I'm actually a bit late. 10 minutes break, and we'll go on with this. So I owe you a few more things about the Fisher information. So I want to make it much more intuitive. Okay, take a break. אני יכול למדל על ידי משפחה פרמטרית, דאטה שלא בהכרח משפחה פרמטרית. אבל איפה בכל הסיטואציה זה היה זה כבר היה בסיפור שהיה בפרקטיקו. בעיקרון אנחנו מדברים על... זה הסטק שלנו. יש משפחה פרמטרית, המשפחה הזאת מייצרת מדגם, ואיזשהו ערך של פרמטרים, ואנחנו מנסים לנחש מה היה הערך של הפרמטרים מתוך המדגם. זה המשפט שחקנו רוב הזמן, עד עכשיו. אז יש לנו את האסטימטור הזה, ואנחנו מנסים למצוא את התטא שמעלה את הרגום. עכשיו פתאום אמרתי, כן, אבל יכול להיות מצב שאתה בעצם לא יודע מה המשפחה. אתה לא יודע מאיפה דאטה. כי אני הנחתי שהלייקליות שלי הוא באיזשהו תטא, כלומר שיש תטא אמיתי, שממנו המדגם נלקח. לא, אני הנחתי שהמדגם, זה מה שכתוב על זה, שהמדגם נלקח באיזשהו תטא. יש כאילו מצב עולם או איזשהו תטא אמיתי, שממנו זה גם תטא. לא חשוב. עוד יכול להיות שהדאטה שלי בכלל לא בא מהסוגיות האלה. יכול להיות שאני חושב שאני רואה גאוסיאן. אבל בעצם הדאטה בא משני גאוסיאנים שהיו מעורבבים ואני לא ידעתי. הדאטה בא מהתרגות מסוימת שאתה לא יודע מה. אתה לא הנחת שאתה יודע מה. כן, אני הנחתי שבא מהמשפחה. כלומר, אני הנחתי שהדאטה בא מהתרגות עבור איזשהו ערך דאטה קטן בתוך הקלאס הזה. זאת המשמעות של המשפט הזה. זאת אומרת שהדאטה בא בגור בערך מסוים של דאטה. אבל התטא הזה מגביל אותי למשפחה הפרמטרית שלו. עכשיו, חשבתי ואמרתי, כן, אבל יכול להיות שהדטה זה בכלל בא מפעילות אחרת. אני חושב שזה פואסון, אבל בעצם זה משהו אחר. מה המקסימום לייקליהוד יעשה במקרה הזה? מה שהמקסימום לייקליהוד יעשה במקרה הזה, זה לא ימצא לי ערך של ההתפלגות האמיתית, כי ההתפלגות האמיתית אני לא מחפש אותה בכלל. תן לי את קירוב הכי טוב במשפחה להתפלגות האמפירית. זה יכול להיות קירוב רע מאוד. יכול להיות שאת מנסה למדל נוירון על ידי תהליך פואסוני, אבל בעצם זה בכלל לא קשור לתהליך פואסוני, זה משהו נקרא יותר שלא לגמרי, אז אתה תמציא את התהליך הפואסוני שמקרב הכי טוב את הנתונים שלו. באיזה מובן מקרב הכי טוב? זה במובן הזה של הדיקל, הוא ייתן לי את ה... זה לא כתוב פה. כן, זה יש לי. זה ייתן לי את הנקודה הקרובה ביותר לדאטה שלי במשפחה הפרמטרית. אני אדע מתוך ה-DKL הזה. אותו אני יכול לשאול. לא. זה התפלגות אמיתית. אני מוצא, יש לי דאטה, בסדר? זה דאטה. יכול להיות כל דבר בעולם. עכשיו המקסימום לייקליהוד הוא ההתפלגות הקרובה ביותר במשפחה אל הדאטה שלי. ואם זה 0, אז אני יודע שהדאטה נמצא במשפחה. אם זה לא 0, אז המרחק הזה, בדיוק המרחק הזה, אומר לי כמה לרחוק מהמשפחה. לא, תטא זה איזשהו פרמטר. אוקיי, זה אולי באמת לא היה ברור. אני רוצה להבין מה בדיוק מפריע לך, יש כאן איזושהי ראייה פרמטר. נניח תחשבי על כל הגאוסיאן, על כל הקפצון. למדה בחזקת M, חלקי N עצרת, E בחזקת מינוס למדה, זאת ההתפלגות ל-M. זה הפרוסון. נניח שאת רואה ספייקר. אני רוצה להביא את זה למשהו שמדבר אליי. ואני מנסה ליצור מה הפילוג הכי קרוב לספייקר שאני רואה בתוך המשפחה הפרוסונית. אז אני אמצא את הלמדה הכי טוב מקרב את הנתונים. אבל אם הנתונים הם לא פרוסוניים, כלומר, אני לא מוכן לתגור אחרת היום. למשל, מתערוב לפני פרוסונים. כל מיני דברים, או סליחה, אני לא רואה נבון אחד, אבל אין נבון. אני אכלף פרטי ספייקר. אז מה שאני אראה אז, אני אראה התפלגות, אז עכשיו, כל הפרוסונים נמצאים על יריעה כזאת. ההתפלגות הכי קרובה לנתונים האמפיריים, זה ההתפלגות שבעצם מזהרת המרחק. לא, תטא זה לא הפרמטר אמיתי, במקרה הזה תטא זה הפרמטר הכי קרוב. זה יכול להיות רחוק מאוד, אם אני נמצא לתוך המשפחה, אז זה יהיה זה שתטא זה איזושהי נקודה, כולם נתיב. אני מחפש נקודה, פי מקסימום לייקליהוד, זה עם התטא מקסימום לייקליהוד שהוא הכי קרוב. הוא ממזער את המרחק הזה. אז פי תטא מקסימום, תטא מקסימום יהיה התטא שממזער את המרחק הזה, כלומר זה הנקודה הקרובה ביותר בתור המשפחה הפרמטרית שלי אל זה. אבל זה לא חייב להיות 0. זה יהיה 0, וגם בכל מקרה זה יהיה 0 רק בחיצות. גם אם לתת לי לקוח מתוך המשפחה הפרמטרית. כל הנוריטי נקרא הבסיסי, המרחק הזה לא יהיה בהכרח 0. הקונסיסטנטיות, פרט הקונסיסטנטיות שהייתה כתובה פה איזשהו מקום, בעצם טענה שבסוף, בגבול שאין לכם סוף, המרחק הזה יהיה 0. אם באמת באתי מהמשפחה. אבל אם לא באתי מהמשפחה, הוא לא יהיה 0 אף פעם. ואני תמיד אשאר על איזה מרחק סופי למשפחה.
אז הקונסיסטנטי רק אם אתה...
נכון, הקונסיסטנטיות זה מושג די חלש. זה קונסיסטנטי רק אם אתה נמצא בתוך משפחה.
The smallest maximum is the region where alpha is larger than beta. It actually takes alpha equals beta.
Okay.
And the opposite when you start from a beta which is larger.
Okay. Yeah. I think I get it. But I need to take a look at why either alpha or either beta.
Yeah.
Okay. I will take a look at it.
sum of the independent. Because of IID. I just realized that the decline reduces visual information doesn't include all okay. But you use the fact that the row gives you a sum, and then because everything is independent and dynamically distributed, so you should do it. Yeah. Yeah, okay.
Okay. All right. So again, I see from the questions that it was a little bit too abstract. So first of all, this issue of projection. So again, I mean, in the general framework that we talk about, we assume that the data actually comes from the parametric family, which means that there is a theta in the parametric family which generates the data. Okay, this is what we call proper estimation. So you actually know that the data, let's say, is Gaussian, and you are trying to estimate the best mean and standard deviation. And then everything that I said, like consistent and all this makes sense, because then eventually you can find the right number, the right parameters. But then I told you, and confused you a little bit, that if I have only a finite sample, then the empirical distribution is not necessarily from the parametric family. Of course not, because it's just, fragments here and there. And then I told you, okay, look, essentially what you do with finite data is you project the empirical distribution on the parametric family. That's what I said here. Which means that out of all the possible parameters, I'm looking for the one which is closest to the empirical distribution. Okay, now, if it is indeed coming from the parametric distribution, then in the limit of large n, this empirical distribution is going to get back into the manifold, because the empirical distribution is going to be as close as possible. But if it's not coming from the parametric distribution, let's say my data actually came from a mixture of two Gaussians, and I'm forcing it to look like a Gaussian, then it will never go back. So even in the limit, it will stay away from the manifold a little bit. And then the maximum likelihood estimate is going to be the closest point in the manifold to the empirical distribution. And that's actually, this is what you usually see. I mean, you have finite data. You assume it's a Gaussian, okay. But if it is indeed a Gaussian, in the limit, this distance is going to shrink to 0. That's what consistency means in the large space. Okay. So now I want to go back to the primer round. So again, I don't want to repeat the proof. You saw it. It was a bit tricky. We used the Cauchy-Schwarz Inequality. Somebody here asked me last time, have you solved the problem that you asked me? Okay, so of course I did it too quickly, but so we actually used the Cauchy-Schwarz Inequality, if you remember, and the Cauchy-Schwarz Inequality was based on the fact that E of x, y square is always less than, E x, y, the product of two variables, is always less than the variance of x, from E of x square times E of y square. which in the case of, if I now subtract the mean, so E of x minus the mean of x times y minus the mean of y, this is square is always less than the variance of x times the variance of y. This is actually something what we call the covariance of square of x and y is less than the product of the variances. So these are all different ways of writing the Cauchy-Schwarz inequality. Why, if this is in general true, this is also true. So I simply subtract, change x to x minus the mean and y to y minus the mean, and then I get this into the variance. Now, in our case, what we actually proved is that the integral of the log p over theta, or the score, times theta hat of x times p of x given theta dx, which was some sort of covariance, x times y, this is x and this is y in some sense. This was less than, by the Cauchy-Schwarz inequality, the variance of the score times the variance of theta. So this is essentially how we proved it. And this was this square. The square of this was less than this, and this was equal 1. So essentially what it proved to us is that the variance of the score times the variance of theta is greater than 1. And from this I got this. Okay. So there was one slight delicate point here, that we used twice the fact that I actually moved from theta hat to the variance of theta hat is because I subtract theta. But when I replace this by theta hat minus theta, but then it's just like adding the average of the score times theta. But the average of score times theta is 0. Why is it 0? Because we proved that the average of the score is 0. So subtracting theta here, or the expectation of theta actually, or theta hat, here doesn't change anything. Just like adding 0. And that's why I could move from the square to the variance. So that was a point that you mentioned last time, and I realized it's probably not clear to anyone. So the fact that I wrote variance here means that I actually subtracted the expectation here. But it's okay because the mean of this was 0. Okay, so that's something I wanted to clarify. So when you go through the proof, make sure that you understand this. I'm using the fact that this has a 0 mean twice. First to write the second order of this as the variance of this. And then to write this as this minus this, which is giving me the variance of this. In both cases, it's the fact that the score has a 0 mean, which makes it. Okay, so that's okay. Now I want to show two things. One of them you are going to have as an exercise. I'm not going to prove it here, but the Fisher information J of theta, I defined it as the expectation with respect to x of the square of the score. Okay? This is the definition that I had. And you'll show that it's also minus the expectation with respect to x of the second derivative. This is an exercise. Okay? And of course, in order to prove this, you're going to use again the fact that the mean of the score was 0. Okay, so this is something I want you to show. You'll get it as a formal exercise. And I'm going to use this. Okay? So now, there are two things I want to show in the remaining half an hour. The first one is, and that theta ml in the limit of n goes to infinity is efficient. The variance of theta ml in this limit is equal to 1 over ng. Okay? And actually, okay, so I already said it, but I'll just say it again. So we call theta hat is called efficient, unbiased. Unbiased theta hat is called efficient if this happens, if the variance of theta hat equals 1 over ng instead. In other words, it achieves inequality in it's a minimum variance. Minimum variance unbiased estimator. Sometimes it's called MVUB, unbiased estimator. Especially in the engineering literature, you're going to see this combination of words, of letters all the time. Minimum variance unbiased. So it's MVUB. Okay, so it's minimum variance unbiased estimate. So in some sense, what this statement is telling us, this claim or proposition or theorem, is telling us that theta ml is asymptotically efficient. Okay? So when n goes to infinity, this is going to happen. So essentially, I mean, okay, so it has to be a little. This is 0 and this is 0. It's not only that they're 0, but essentially what I'm going to show is something more delicate than this. It's slightly more than asymptotic. I'm actually going to show that in the limit, the probability of theta ml in the limit is going to have a normal, to look like a normal distribution around theta with variance which is 1 over ng. So this notation, which I've already used before, this is normal. So this stands for Gaussian or normal distribution. This means that the mean is going to be the 2 theta, so it's unbiased, and the variance is going to be exactly 1 over ng. So this is the sigma. This is mu and sigma square of the variance. So essentially, so I'm going to show even more than what I said before. What I said before is really asymptotic, but asymptotic here is meaningless because n goes to infinity, everything goes to 0. I'm actually telling you that it's going to approach a normal distribution. So essentially, theta ml is going to be normally distributed around the true parameter with variance which is exactly the minimum possible, which is the n.
Only for the limit.
In the limit. So it's asymptotically, yeah, when n is large enough. But you see there's a slightly different. Instead of calling, when n goes to 0 to infinity, and this actually goes to a delta function, so it's actually meaningless. But even before that, it's going to look like a Gaussian. So it's going to behave like a Gaussian with a width which is. So this is the first thing I want to show, and then I'm going to characterize all the probability distribution which are efficient in the sense that they have efficient estimates. These are going to be, to some of you, unsurprisingly, I hope, exactly the exponential families. Okay, the exponential families are very, very important in our story. So how is this proved? So first of all, intuitively, you already know that the log likelihood, so this is something which I call L of theta given xn, which is what? It's just 1 over n. It's the log of pxn given theta. But again, when I think about it, so this is simply the log likelihood. before I can normalize it by n. But if I normalize it by n, okay, but what do you know about it? This is a sum. This is a sum of log pxi given theta. But since the xi are assumed IIDs, so this is again xn, unless said otherwise, is our IID distributant from the same theta. So this is the sum of IID numbers. And what do we know about sums of IID numbers in general? If I correctly normalize them, they're going to approach the expected value. This we know, of course. Okay, so this I already used. I used it when I proved consistency, that it's going to approach the expected value. But now I want to actually think about the distribution itself. So remember, if you have sum of IID numbers, how it's going to approach in the what we call the law of the central limit theorem. The central limit theorem is going to approach a Gaussian, but under what conditions? So it's going to approach a Gaussian. It's going to look like something, if I actually subtract it from the mean, so it's going to center around the mean of this, which I already know what it is. But it's going to, what's going to be the width of the Gaussian? Yeah, so in order to actually see that this is going to approach a normal, I need to estimate it around the mean. Let's see, in some sense, in what sense it's mean, and then I have to normalize it by 1 over square root of root. And so I know that this is going to approach a normal distribution around something, the true theta, around the log likelihood of the true theta, they call the L of theta, with something which is proportional to square root of n. This is what essentially the central limit theorem is telling us. So intuitively, this looks like something that makes sense because it's simply central limit theorem. Okay, but now I want to prove it much more carefully. So the idea is actually a bit tricky, but I hope you and swallow the tricks. So I look at this L of theta as a function of xn, okay? And I actually want to Taylor expand not L of theta, but L prime of L of theta. So the derivative, L prime of L of theta is just the Fisher score. It's d log p x theta to d theta. This is just what I call L prime, okay? So just to save some my fingers, I'm writing it as L prime theta, okay?
Can you explain the difference between the first L and the L inside the normal distribution? The L of theta giving x and the L of theta?
Yeah.
What do you mean by L of theta?
So this is a sum of IID numbers. They're going to center around their mean. Now, if it's unbiased, yeah, you're right. This is the true theta, and this is any theta, okay? So they're going to center around the L of the true theta. Yeah, that's what I mean by that. This is because it's unbiased. This is going to be the mean. So the log likelihood is going to center around the true log likelihood, and the variance. We're going to see what this coefficient here is exactly going to be the Fisher information, of course. Okay, so I'm now taking this L prime at some value, let's call it theta prime, just to make sure that at theta prime, yes.
This is the actual proof?
Yes, yeah, so this is the proof. I'm expanding it in a Taylor series. So this is really where it's become a little tricky. So I'm expanding it around theta. So this is L prime of theta. So this is a Taylor expansion. Taylor Taylor expansion around theta. Okay, so just to remind you, if you expand the function around some x0, so it's f of x0 plus f prime of x0 times x minus x0 plus higher order terms. Okay, this is Taylor. This is what I call first order Taylor expansion. Okay, just to remind you. Okay, this is always true if f is differentiable. So I'm expanding, but the function that I'm expanding is the derivative. It's actually the Fisher's score. So I'm expanding it in theta prime around theta. So this is the first term. Plus what? Plus the derivative of L prime, which is L double prime, of theta times theta prime minus theta plus higher order terms. Okay? So this is just Taylor expansion around theta. Now remember, theta is the true theta. Okay? So this is always true. This is just using this equation, but where f is actually L prime, or the Fisher's score. Okay, now I plug theta ml here. So this gives me that L prime of theta ml. Theta ml is just a number not too far from theta, hopefully, because I know it's in the limit, it's not too far from theta, so this expansion makes sense. So L prime of theta ml is equal to L prime of theta plus L double prime of theta. You see the L prime of theta is exactly this. It's the second derivative. L double prime of theta, theta ml minus theta plus higher order terms. Okay? But what is theta prime at theta ml? What is this L prime at theta ml? It is the maximum likelihood. How is the maximum defined? It's exactly the thing that where the derivative is 0. Remember, this is all as a function of the data also. There's a data there, just suppress it.
Can you repeat that?
Now, so theta ml was defined, where should I write it? The derivative of log p xn to theta at theta ml is 0. This is the way theta ml is defined. Okay? I know where so I'm using it here. So this is 0. Okay? So theta, the derivative with respect to theta at theta ml of the log likelihood of the data is 0 because I'm at the maximum likelihood. Since I'm at the maximum likelihood, the derivative is 0 there. Okay, that's the definition of maximum likelihood. This is what I just wrote here. Okay, so in this short notation, this is 0. So what I get out of here is that theta ml minus theta, the whole thing is 0, is minus L prime of theta divided by L double prime of theta. Okay?
Why is it minus?
Why is it minus? Because I moved this to this side. Okay? So theta ml minus theta looks like this over this. Now, remember that eventually what we want to show is that theta ml minus theta looks like a normal distribution with a square root with some function that depends on like a normal distribution with a square root. So essentially what I have to do is to look at this so square root of n theta ml minus theta looks like minus 1 over square root of n L prime of theta divided by 1 over n of L double prime of theta. Okay, so remember this. All I did is multiply by square root of n here. So square root of n, this is the thing that eventually is going to look like an normal variable. Now, okay, so now I'm actually using again Amir's notation. I don't know if you looked at his notes or not. Now, my argument is that this variable looks very much like a Gaussian, whose width is exactly the Fisher information. So we know that 1 over n. So now look again at this log likelihood. Let me just make sure that I write it in exactly the same way. This is the only thing I wanted to look at the notes here. So we
Why would you multiply by
no, because okay, so I know that theta ml I know that the log likelihood ratio is actually a sum of n random variables. So essentially what you want is to divide everything. You want to divide the log likelihood ratio by n. So again, in the central limit theorem, let me again just say it in the right way. So there's a minus sign here. Minus sign here. I need this minus sign because I need the second derivative. So the first term, this L prime square root of n of L times theta is exactly, 1 over square root of n L times theta. The denominator is exactly the 1 over n, the sum that I go from 1 to n of the score or the log pxi even theta to d theta. And this is this is square root of n so this is this is square root of n, the expectation of d log pxi over theta, which is what? What is the expectation of the score? 0. So this is 0. Okay, so we know that theta hat minus theta is going to center around 0. But what's going to be the variance? So 1 over n L prime of theta hat is precisely 1 over n, the sum I go from 1 to n of the d square log pxi theta to d theta squared. Okay? But from the exercise that I want you to show, from this is precisely with the minus sign. So this is minus this is precisely the Fisher information. So this is from the exercise. Okay. So essentially what we got is that theta, square root of n, theta ml minus theta, is going to be centered around 0 with a variance which is precisely the Fisher information. So this is what's written here. So it looks like something which is centered around 0 And the variance is precisely this number, sigma square. So this is this essentially proves the theorem. I mean, so theta ml is going to behave like a normal distribution with zero mean, with theta mean, because it was theta ml minus theta, so it's going to have theta mean and 1 over nj. So this is 1 over nj here. It's 1 over nj variance. Okay. Now notice one thing. Should all you know what the Hessian matrix is? You know that the second derivative of a Gaussian at the peak is what? If you look at the Gaussian, just to remind you this, if you look at the Gaussian, Px of mu and sigma, and this is 1 over 2 pi sigma square e to the minus x minus mu square over 2 sigma square. So the log of it, log p x mu sigma is this minus ln 2 pi sigma square minus half ln 2 pi sigma square. This is this normalization minus x minus mu square over 2 sigma square. So I simply took the log. And now if we take the derivative, I'm calculating actually the Fisher information for the Gaussian. So if we take the derivative with respect to x. So essentially, yeah, okay, so you see that essentially the second derivative, so again, if you look at this as the beginning of a Taylor expansion in x. Taylor expansion in x, you see that the second derivative, the square log px mu sigma to dx square, or the second term here, this is so the first derivative is x minus mu, the 2 is going to fall with the 2, and the second derivative is simply 1 over sigma square. So this is called the Hessian matrix in general. When you have multidimensional, in this case it's simply the second derivative. So if you look again at the Gaussian is is an exponent of a parabola, and so if the log is just a parabola, which is centered around mu, and the sigma is simply the second derivative of this parabola at the peak. So you see again that the variance of a Gaussian is simply related to the second derivative at the peak. Now we are talking about the variance in the parameter space. So instead of x, I have to think about it in terms of theta, and this second derivative with respect to theta is simply the width of the Gaussian at the peak. So the second derivative of a Gaussian, of the log Gaussian distribution, is just the width. Okay, so you see that the Gaussian distribution is exponent of a parabola. I take the log, I get a parabola. I take two derivatives with respect to x, I get 1 over sigma square. So this is really this intuition that the second derivative here is, if this was a Gaussian, the second derivative is just 1 over sigma square. And that's exactly what we see. Okay? Yes?
Why is the denominator in the right?
Again, that's what I was just trying to say. So we're talking about a distribution in theta. Okay, so instead of x, I'm talking about theta now. I should have said it. Okay, this is theta. This is theta prime, and this is so this is theta ml, theta prime, and mu here is the true theta, and sigma is simply the variance of a Gaussian. So you see that the variance of a Gaussian is the second derivative replaced by theta m. This I managed to confuse you. The second derivative of a Gaussian, of the log of the Gaussian, is simply 1 over the variance. How do you see it? Because I have a constant, and I'm now taking derivative with respect to this variable, okay, theta. So the first derivative kills this, and I get 2 from here. So it's the derivative of theta minus mu squared, so it's 2 mu theta minus mu divided by sigma squared. And then I take another derivative, and I get 1 over sigma squared. So the second derivative of a parabola is always the width, the coefficient. I don't know how to say it most. You have a parabola. So this is a Gaussian is an exponent of a parabola. So if I take the log, I get the parabola. And the second derivative of a parabola at the peak is what? So you see parabola here, okay? A parabola centered around mu. Now take one derivative with respect to theta. You get 2 theta minus mu over 2 sigma squared, the 2 cancel. Take another derivative, it's 1 over sigma squared. Okay, because I have a theta over sigma, theta minus mu over sigma squared. I take another derivative of theta, I get the mu over sigma squared disappears, and I get so 2 derivatives of this. Yeah, so I get theta minus the mu of theta square over 2 sigma squared. The first derivative is 2 theta minus mu over 2 sigma squared, which is just this, and the second derivative, this is the first derivative with respect to theta. The second derivative with respect to theta is simply 1 over sigma squared. You see this? Yeah. Okay. So 1 over sigma squared is precisely the second derivative of the log likelihood function. So this is precisely why the second derivative gives me the variance of a Gaussian. The second derivative at the peak is the variance.
So I times n?
Now the n is simply the normalization here. You see that without the square root of n, I need the square. So I know that if I have sum of IID numbers, in order to actually see a Gaussian, I have to normalize by 1 over square root of n. So essentially what we did here is we multiply by square root of n this, and which is the same as multiply by 1 over n here and 1 over square root of n here. It's the same thing because the n goes and I get square root of n. Okay. Now I showed you here that 1 over n this is precisely square root of n, the mean of this, which was 0. Okay, so that's fine. That's essentially telling me again the consistency, where it's going to be unbiased at the end. But the 1 over n here gives me the average. I need a 1 over n in order to get the average of the second derivative is a minus sign. But the average of the second derivative is just deficient information if you believe this. Okay, this you're going to show. And once you show this, you have completed this. Yes?
But I don't really understand it, because if we wanted to approximate any estimator to a Gaussian, so we could use an extension, a Taylor extension over theta, right? Okay. And
so there's only one place. You're absolutely right. Or there's one place I actually use the fact that it's maximum likelihood.
Yeah, but for the 0.
For the 0. Yeah.
Otherwise,
it's true for any estimator. Yeah.
But if we're using only the mean as L prime and the variance as L double prime, so I don't understand why we need the last equality. So it just says that we can approximate any estimator in this way, and then I don't understand why we use the theta ml minus theta equals the ratio, this ratio.
Okay, so again, we use it exactly in one place here. So this is true as long as I didn't put it to 0. It's true for any estimator. Now, in order for this to be true, I use the fact that it's 0. And then I showed you that theta ml minus theta looks like 0, something that approaches 0 at the end. Over the variance. So this looks like essentially x minus mu. This is the x minus mu square. divided by the sigma square. Yeah. So this looks like x minus mu, so that's why it's approaching 0, divided by sigma square. And what the whole exercise here was not to show you that theta ml is centered around theta. This we knew already, because it's consistent. Symptotically, it's going to be centered around theta. But what I really wanted is to find the variance. So the variance, this is this L double prime here. So this is okay. This is some number. Okay, I don't care about it. Which eventually are going to approach 0 because it's in the limit consistent. But the variance, this is what I really cared about, is precisely the Fisher information. So where did you use the fact that I used the fact that it's theta ml in order to write this equality?
Yeah, but shouldn't we, if we want to calculate the variance, shouldn't we take it like a square and the expected value of this ratio?
No, I actually. So what I'm saying, I looked at the log likelihood distribution and I said that the log